Alright, last time we saw 3 criteria to get the initial BF solution. This lecture, I will talk about how to test the initial solution is the optimal, which is optimal test, which means check whether the initial solution is optimal. Using the notation of above table, we can reduce the standard optimality test for the simplex method to the following 4 transportation problem. The optimality test. A basic feasible solution is optimal if and only if the value of Cij minus Ui minus Vj is larger than 0 for every ij such that Xij is non-basic. First, step 1, derivation of the values of Ui and Vj for the current BF solution. Since the value of Cij minus Ui minus Vj is required to be 0 if Xij is a basic variable, Ui and Vj satisfy the set of equation Cij equals Ui plus Vj for each ij such that Xij is a basic variable. There are m plus n minus 1 basic variables, and so there are m plus n minus 1 of these equations. The number of n nodes are more than this one. So one of these variables can be assigned a value without violating the equation. A convenient choice for this purpose is to select Ui that has the largest number of allocations in the table and assign to it the value 0. I will illustrate it in this table. We setting U3 to be 0. Here to be 0. Then you can see that here 0, the 19 minus 0 is 19. Use this equation. For the U3 plus V1 is 19. So here the V1 is 19. Then also 19 minus 0 here is 19. And 23 minus 0, 23. Okay. 90, and here is 14. 14 minus 19 is minus 5. And the same to this one, and this one. We do it like all similarly. Okay. The step 2, calculate and fill in the variable of, we denote this value with sigma ij. Then we will calculate the sigma ij for each non-basic variable xij, such that here 90 plus minus 5 is 15. Then 16 minus 19 is 2. This is the sigma ij for this non-basic variable x11. Similarly, 19 plus is 15 and 16 minus 14 is 2. Similarly, it's 0, and then we can fill all the cells without a circled allocation. That is the non-basic variable. Okay, we are now in a position to apply the optimality test by checking the values of non-circled number cell, because 2 of these are minus. So the initial BF solution is not optimal. Then we go to the third step, iteration, which is determine an empty basic variables, a living basic variables, and then identify the resulting new BF solution. Since sigma ij represents the rate at which the objective function will change as the non-basic variable xij is increased, the anti-basic variable must have a negative value to decrease the total cost z. So the iteration will begin by determining the entering basic variables. We selected the non-basic variable xij have the highest value of is in absolute terms. Then the sigma ij value of non-basic value in this table, the sigma ij here is -2 and here's -1, so the absolute term is bigger. It's here. So we choose x25b entering variable, this one. Then go to the step 2, determine the living basic variable. Identifying the chain reaction required to retain feasibility where the entering basic variable is increased. After the chain reaction is identified, the donor cell having the smallest allocation automatically provides the living basic variable. In general, there always is just one chain reaction that can be completed successfully to maintain feasibility when entering basic variables is increased for 0. So now we identify the chain reaction with this table. This is the entering variable x25. To maintain the balance, increase the location of x25. It needs to decrease the amount in this place, and this increase, decrease. So we give this chain reaction. The net result in the cell 25 and 1,3 become receptive cell, each receiving its additional allocation from 1, 5 and 2, 3. Each donor cell decreases its allocation by exactly the same amount as the entering basic variable, and the other receptor cell is increased. Therefore, the donor cell that starts with the smallest allocation, here is 10, and it's 13. So we give the x25 the 10 and convert and let x15 leaving the basic variables, and the variable x25 entering be entering, it's be leaving basic variables. Okay, the 3 step, determine the new BF solution. We add the value of the leaving basic variables to a location for recept cell, subtract this value from the allocation for each donor cell. Then the simplex tabular becomes this. The leaving basic variable is x15 is 10. So add 10 to the allocation for each recept cell. Subtract 10 for the allocation for each donor, and we get this matrix. The 10 transfer here. Okay, continue the procedure. The major ward district problem yield the complete set of the transportation simplex table shown in this table. This is also related solution. Okay, and this is another. We found here is also a minus, so it needed to iterate again. Okay, now let's see this table. All the sigma ij of non-circular number cell is, they are no negative. So this is the optimal solution of the problem. Okay, now I will summarize the transportation simplex method. First, we need to get an initial BF solution. Second, deriving UI and VG by selecting the law having the largest number of locations, setting its UI equals 0, and then solving the set of equations for each ij such that xij is basic. And then if this value for every non-basic variable is more than 0, then the current solution is optimal and we do stop. Otherwise, go to the iteration. This is the optimality test process. Iteration. The iteration includes 4 steps. It contains determining the entering basic variable, determining the leaving basic variable, determining the new BF solution, and continue to apply this procedure until the Cij, all the list values are non-negative in the table. Then we get the optimal solution. Okay, that's all for today's lecture. Thank you.